Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the chapter of microwave engineering where we are having the analysis of how the microwave transmission takes place with the help of a single conductor transmission line called as circular waveguide here. So the circular waveguide is of course a hollow metallic tube having this circular cross section. So we started this chapter to see first of all what exactly the coaxial transmission line, a conventional type of transmission line is, and then we have shifted to the knowledge of circular waveguide. We have found solutions to the wave equation while the microwave is propagating inside the cavity of circular waveguide filled with certain dielectric material, most possibly the air or free space that is considered here. Now with the knowledge of having the TEM mode not possible, we have shifted to that of the transverse electric mode. We have solved two of the problems. Now let us have analysis of how the wave propagation take place in the transverse magnetic mode. Let us begin with. So as in the earlier case of transverse electric mode, we have designated the representation T suffix NP here, where N has given us the number of full cycles corresponding to the field vectors and P corresponds to the pth root of nth order Bessel's function represented. Now, as we have to deal with the TM modes here, in the similar fashion, we have the notation of transverse magnetic TM suffix, the same here we have NP here. Now, as we have transverse magnetic, so for electric and magnetic field component, if we have in the cylindrical coordinate system ER, E phi, Ez, then HR, H phi and Hz. So for TE we have initially Ez equal to 0 and we have used the Helmholtz equation for wave equation of Hz to have the derivation of the rest of the other field components here. Now the case is reverse as we are dealing with Tm suffix Np here. So for transverse magnetic we keep Hz to be equal to 0 and Ez will be the existing along with the other field components here. So let us continue the derivation considering Hz is equal to 0 and the Helmholtz equation corresponding to that of the Ez component here. So here we have the form of Helmholtz equation and this is for the Ez component represented as del square Ez is equal to gamma square Ez. Let this can be the equation number 1. Now here del square operated over the Ez component. So del square is the Laplacian operator. So the Laplacian operator most possibly gives us the scalar representation of Ez here. Now gamma square is the gamma, basically the propagation constant accounted for the attenuation measure as well as the phase shift measure here. Now if you want to have solution to such a type of equation where the del square can be expanded into the second order partial differential equations, the solution can be assumed to be of the form Ez is equal to, we have E suffix 0 times Z, the peak amplitude, into the Bessel's function Jn over the cutoff wave number Kc into R here. R is the radial distance measured from the central axis of the circular waveguide here, and it is in multiplication further to the cosine trigonometric function over n times phi in multiplication to e to the power minus j times beta suffix g into z to show the harmonic for the wave changes here. So this can be regarded as equation number 2 here. So this solution of the form of the RHS is of course subject to the application of boundary conditions. So we talk about the boundary conditions because whenever a microwave, which is basically the electromagnetic wave, will be incidenting onto the inside walls of the circular waveguide, the wall body is made up of a metal, most possibly having the highest amount of conductivity there. Inside there, either it is air or having some certain another dielectric material, so that is a different here. Hence the application of boundary condition is very important. Ideally we don't want any of the electromagnetic wave to penetrate the perfect conductive material. So practically there may be certain depth to which it may extend to. With the help of the skin depth we can determine that particular value, but practically it will be very small, so it will be allowing the internal reflection. Now for the application of boundary condition, as such we can consider that the EZ component at R is equal to A will get vanish. And basically the EZ component, so Z being the direction of progress of the microwave inside, so it is along the axis here. So this is very obvious condition here, but it gives us the function j suffix n as a function of kc into a we replace in the place of small r is equal to 0. Now since the jc, the jn function basically over kc of r is the oscillatory function here, so that time there will be a possibility of infinite number of roots, infinite number of roots of j suffix n over kc into r here. So few of the roots we shall be summarizing with the help of the following table. So this table will be giving us the pth root or pth zeros we can say for this function j suffix n over kc into a. So it is the boundary wall of the circular waveguide, and this is corresponding to the transverse magnetic mode having n suffix p into the subscript here, np in the subscript. So we get the first row corresponding to the value of p in the first column as 1 2 3 then 4 we go for. Next to that we can have the order n is equal to 0 for the first column, and this is equal to 1 for the second column. Then we can have 2, we can have the value 3, and so on we can go for. So for the first three columns we shall be discussing here. So for the order of Bessel's function j suffix n, so it will be j suffix 0 with the first root we have the value 2.405. For the second root we have the value 5.520. For the third root we have 8.640, and for the fourth root we have 11.792. For the first order Bessel's function j suffix 1 we can have the first root value is 3.832, whereas the second root value is 7.106, the third root value is 10.173, the fourth root value is 13.324. For the second order functions that we usually deal with, we have the first root given by 5.136, second one 8.417, third one 11.620, the fourth one 14.796 here. So this way we have all the values, and with the increase into the order n is equal to 3 4 5, if we go for the corresponding pth roots here we get the values increased here. So here it is 2.405 increased to 3.832. If we switch from 0th order to that of the first order. To the second order, it rises again 5.136 here. So in this particular scenario, the observation we have for n number of roots obtained. So here we have marked the smallest possible value 2.405 for n is equal to 0 and p is equal to 1. Hence, for the transverse magnetic mode of microwave propagation, we represent it as Tm suffix 01. But as far as the dominant mode is concerned, we have gone through the field equations corresponding to the transverse electric mode. So for transverse electric mode, for TE11, we have obtained the root value for x dash np, we can say in general. So it was obtained to be 1.841, smaller than this one, that it is 2.405. Hence this one is treated as the dominant mode of wave propagation in the circular waveguide here. Now we continue our derivation. As we are with the transverse magnetic mode, we shall be having a substitution of Hz to be equal to 0, and also the partial differentiation with respect to the Z parameter, Z being the direction of propagation, we get it replaced into the complex representation by minus j beta suffix g here. So now these two substitutions to the above equation, and further the use of Maxwell's curl equation as del bar cross of E bar is equal to, in the frequency domain, minus of j omega mu into capital H bar, and another one del bar cross of H bar is equal to j omega epsilon capital E bar. We can have these curl equations expanded in the forms of ER, E phi, EZ, HR, H phi, HZ, and these can also be resolved into the corresponding three components. So very first of all, the first component, we can express E suffix R as minus of j times beta suffix g divided by kc square in multiplication to the partial differentiation with respect to R for the Ez component. Next component, E phi, can be expressed in terms of Ez as we have minus of j times beta suffix g divided by kc square here. We have the partial differentiation with respect to the phi also in multiplication to 1 by R for Ez component again. So we have the Ez equation as before represented for the Helmholtz condition and the solution form here. Next to that, for magnetic we have HR component expressed as j omega epsilon divided by kc square into 1 by R del phi of capital E suffix z. Next to that, we have H phi component expressed as j omega epsilon divided by kc square in multiplication to del R of capital E suffix z here, and as it is transverse magnetic, we have Hz component is equal to 0. So these are the four components into the corresponding radial direction and the angular direction phi for electric and for the magnetic equations here. Now in all these equations we have the use of wave number at cutoff, that it is kc. So it is the substitution for kc square for omega square mu epsilon minus beta suffix g squared here. And let us have the differentiation for the equation of Ez and the substitution of the results into the last four equations for Er, E phi, HR and H phi here. So we obtain Er equation as we have E suffix 0 R here, the peak amplitude in multiplication to here we have Jn dash of x np into r divided by a into cosine of n phi into e to the power minus of j times beta suffix g into z here. Whereas e phi component, e phi is equal to capital E suffix 0 phi into jn as a function of, we have x suffix np r divided by a into the sine function of n phi e to the power minus j times beta suffix g into z here. So these are the two important components, and the equation Ez continues of the form as e suffix 0 z jn as a function of x suffix np into r divided by a into the cosine of n phi e to the power minus j times beta suffix g into z. So these are the three respective components of electric field intensity vector. Now for the magnetic field intensity vector, we have the first component hr expressed as capital E suffix 0 phi divided by the impedance inside the waveguide z suffix g in multiplication to, here we have the basis function jn over x suffix np into r divided by small a. This is in multiplication to the trigonometric function sine of, we have n phi, and the harmonics represented for the spatial variations and the phase shift minus j times beta suffix g into the z here. We have the second component of magnetic field intensity h phi expressed in the form capital E suffix 0 r here divided by the impedance inside the waveguide, the wave impedance zg into, here we have jn dash as a function of x suffix np into r divided by small a into the cosine of n phi here e to the power minus of j times beta suffix g into z component here, whereas the hz component is ideally equal to 0. So in these equations, the impedance that we have introduced, the wave impedance z suffix g inside the waveguide, is the ratio of the maximum of the er component to that of the h phi component. And if you reverse the order, that it is first of all taking the e phi component and then hr component, a negation is to be opted here, and this is in place of beta suffix g divided by omega epsilon. So this wave impedance is along with the substitution for, we have the cutoff wave number kc expressed as the pth root of nth order basis function x suffix np divided by small a being the radius of the circular waveguide dimension. We have the small n represented the nth order that can range from 0, 1, 2, 3 and so on, whereas pth root stands for 1, 2, 3 and so on. At last, after derivation of all the field vector components into the r, the radial direction, the phi angular direction, and the z component here, the direction of propagation of microwave, it is necessary to address few of the performance components, the measures as far as the propagation is concerned, in the terms of velocity if you can take, in the terms of impedance you can take, or the phase shift constant you can take. So we have addressed it before in the TE modes in circular waveguide, but few of the constants are same, but few are having certain changes. So here we go for the first component for the transverse magnetic mode. Here we have the phase shift constant beta suffix g accounting for the propagation, giving y square root of, we have omega square mu epsilon minus x suffix np divided by small a. So this is squared here. Next to that we have kc, the wave number. Just now we have written x suffix np by a obtained by omega suffix c, the cutoff value, in multiplication to the square root of mu epsilon here. Whereas the cutoff frequency fc is obtained as, we have capital X suffix np divided by, we have 2 pi small a, the radial dimension of circular waveguide, into square root of mu epsilon. After the cutoff frequency, we have the phase velocity inside the waveguide, hence we represent it by v suffix g. It is the ratio of angular frequency omega to that of the phase shift constant beta suffix g. So it is obtained as the phase velocity in the unbound medium divided by, we have square root of 1 minus fc by f, bracket is squared. And lastly, the wave impedance inside the waveguide z suffix g is the ratio of, we have beta suffix g divided by omega epsilon is equal to eta in multiplication to the square root of 1 minus fc by f, bracket is squared. So here we have eta to be the intrinsic impedance calculated for the medium, the square root of mu by epsilon. So this is in the under root here. So we have addressed that though we have formulated the field components for electric and magnetic for transverse magnetic mode, to compare it with that of the TE mode, we have the TE11 mode to be the dominant mode for the circular waveguide. So in the next lecture, to see this much of knowledge for transverse magnetic mode of wave propagation, we shall be having a practice of problem number 1 for TM modes in circular waveguides. So I hope you are definitely enjoying the learning with microwave engineering topics. For more such information, you can subscribe to Ekeeda channel. Thank you.